tonight's lectures, we're going to branch out now. We're still going to be talking about linear problems, but we're going to be talking about problems specifically using integer and binary variables. And binary variables in particular are very useful to us because they allow us to do something that we really need to do, and that is have the ability to turn things on and off, right? So when you think of binary numbers, you think of zeros and ones, right? Well, think about that in a linear sense then. If I have a linear equation where one of my variables is a 0 or a 1, then if I'm using that variable to multiply a number, sometimes that number is going to be 100%, sometimes it's going to be 0, right? Where might that come in useful? Can you think of an example where that might come in useful? Well, I'll give you one that jumps up in supply chain all the time, and that is figuring out whether or not to open a distribution center. All right, if I have a distribution center, it's going to have fixed costs and variable costs. Well, if the distribution center is open, I'm going to incur the fixed costs for sure, and then whatever volume I ship through it will be a variable cost. But if I choose not to open that, then my fixed cost is, by definition, going to be 0. And I should have also the 0 variable cost, which means I have 0 capacity from that distribution center. So that's a situation where having binary variables is useful. You see it modeled a lot of times when we're talking about using machinery, for example, or when we're talking about any kind of a management decision where we can either go, no-go type of decision. We're going to start off, though, by looking at what's known as a transportation model. And transportation models are a subset of these distribution models that I was talking about. And they're very simple. Basically, what they say is, I want to ship, in this case, from a plant, one of the 3 plants that you see listed here, to one of these 4 regions. Now, ordinarily, this problem is going to depend on 2 things. It's going to depend on the cost of the shipment, and it's going to depend on the capacity of the production plant. So when you look at these costs, you should think of these costs in terms of mileage or in terms of distance or something like that. So theoretically, at least, the distance from plant 1 to region 1 is shorter than it is from plant 1 to region 3, because the cost to ship to region 1 is about half the cost of shipping to region 3. Does that make sense to you? Okay. In addition, we have a situation where our plants have a fixed capacity, and those capacities are the numbers you see there. Now, each one of the regions also has some amount of demand, and these are the demands you see here. So we can start off solving this problem without even using that Microsoft Solver or Excel Solver, right? Let's come up with a feasible solution that we know is a good solution, all right? And what would be a characteristic of a good solution? What are we trying to accomplish here? We're trying to minimize the cost. So how would we go about, without using Solver, how would we go about coming up with a good way to minimize the cost? Exactly. What he said was, look at your cost table here and figure out where the lowest cost is to start with. All right? So what's the lowest cost to start with? 120. It's plant 1 to region 4. So, oh, there's a 116? I'm sorry. Yeah, there is a 116. Okay, so there's 116. Plant 2 to region 2. All right? So, what we would want to do then is we would want to satisfy the demand at that cost if we can. Well, it turns out plant 2 has capacity of 600, so if we only ship 200, we've satisfied demand. Let's just go ahead and fill out these bottom rows here. What are these going to be? These are going to be sums, right? Let's go ahead and do the sums here. And these are going to be sums also, right? Okay, so now we've shipped 200 from plant 2 to region 2 at the lowest cost we can find, and we satisfied all the demand, right? So we can go through this iteratively, picking up the next lowest cost, which now is the 120, right? So we could pick up 300 here. And then what's the next lowest cost? 122, is that right? So 122, 300 there. All right. And now, since we've satisfied demand for 3 out of the 4 regions, all we have to do now is satisfy demand in region 1. So the lowest cost in region 1 is the 131. So I'll pick 150 from there. That uses up all of the capacity of plant number 1. I still need 300 though, don't I? My next lowest cost is 178, but I can't use that 300, can I? Because I've already used it up. So I'm forced now to pick up the additional 300 here. Oh, I'm sorry. I was looking at the wrong number, wasn't I? 200 there, and then 100 there. Okay. So now that's my solution. And I did it without using solver. Right? So let's see what the cost of this solution is. The cost is going to have to be equal to, what formula am I going to use, do you think? Sum product, right. I'm going to use the sum product of the units shipped and the costs. And the answer that I get is $176,050. Okay? Now, this is how transportation problems work when you're trying to minimize cost. We did it kind of intuitively, choosing the lowest possible cost. The problem is we don't know whether there's some trade-offs in that cost table. In other words, might we be better off shipping to a particular region at a slightly higher cost to free up capacity to ship to another region at a cost that's still lower than any other cost to that region? We don't know that. So what I'm going to do now is I'm going to go ahead and I'm going to create this as a decision model using Solver. So first of all, what's my objective function? Well, first of all, what are my decision variables? That's what I really need to start with, right? What are my decision variables? My decision variables are the amounts that I ship from each plant to each region. So I'm going to go ahead and highlight those as decision variables. My objective function is right there. My sets, there's a set right there. And then I've also got some parameters here. And then what kind of constraints are they? Well, they're all on the capacity side, less than or equal to constraints, correct? What about the demand side? What kind of constraints are those? Which is it, less than or greater than? Greater than or equal to. Okay, so now I'm ready to set up my solver model. My solver model says, there's my objective function. I want to minimize it. I want to do that by changing the cells in this table, subject to the following constraints. These values are less than or equal to these values, and these values are greater than or equal to these other values. Do I need to have my non-negativity constraint for this as well? Why? Because otherwise I'd ship negative quantities and that would reduce my cost, right? Plus it would increase my capacity if I ship negative quantities. And so finally, I'm going to choose the LP simplex model. Now, before I hit solve, let's remember that answer, 176,050. And let's see what we get. Well, golly, we still got 176,050. Is that what you got? How about that? We solved it without solver and got the same answer as with solver. Will this always be the case? Just so happened it was this time. Could we get another solution that also came out to 176.50? Well, the answer is yes. Now, maybe in this problem, it wouldn't happen, but I have seen many transportation problems where you can have multiple answers that all come up with the same objective function. Doesn't that violate optimization? No, not at all. Just says you have multiple optimal solutions. The point is, none of those solutions is better than this one. So you can have different decision variables, but as long as they have the same objective function value, then it's considered a multiple optimal solution case. That is correct. The objective function in this case is the lowest possible cost looking at all scenarios. What other questions do you have? Okay, well, the one thing that we can point out here without going into too much additional detail is that there's at least one plant that has unused capacity, right? Plant number 2. And so it might be worth understanding whether or not some of the solution would shift away from plant 2 if there were additional capacity at the other plants. for example, what I'm what I'm questioning here. All right, we already know that this 200 is the lowest shipping cost to region 2, right? But you'll notice 131 is the lowest shipping cost to region 1. And you wonder if maybe if region 1 had additional capacity, if there would be a better solution. Or if plant number 3 had additional capacity, would there be a better solution? Because clearly either one of those cases would be better than using the plant 2 capacity to ship to region 1. How would you answer that question? Well, all right, so he asked me to repeat the question. Let me back up a minute, okay? I asked a question because I already had an economic model in my mind of what I'm trying to understand with this problem, okay? But why would I have built this model in the first place? Would it be just to make sure that I got the lowest possible shipping cost each of those plants, each of those regions, rather? It might be. I mean, if it's a big enough transportation model, that could be the case. But I'm asking, what other economic insight would I want to gain from this model? And why would that be? Sure, sure, sure. But in any event, this what prompted my question to you was looking at the costs of shipping to region 1 and noting that I had to use plant number 2 to ship to region 1, right? That's the only way I could satisfy demand because I had already filled up the capacities of the other plants. But the cost to ship from plant 2 to region 1 is so much greater than the other two regions. I mean, even 178, that's almost $75 cheaper than from plant number 2. So my question is, how is there a way that I can take advantage of a lower shipping cost? Well, the only way I know to do that would be to change the capacity of one of the other two plants. And so that's why I'm asking the question. What insight can I gain from this model? And that's the question you want to ask with all of these models that we're building. What is the insight that I can gain? In most cases, there's going to be an economic cost associated with it, or an economic insight that you're going to want to get from it. In some cases, it may not be economic. It may be another measure of well-being. But in any event, we don't want to just stop with the model. As good as this model is, we could have done equally well on our own. I just proved that to you, right? But how easy would it be for me to take the next step now and say, okay, well, if I could get different capacities out of the other plants, how much better off would I be? Let's just do the simple math. 250 minus 178 is, was that 72? Is that right? So for every additional unit I add to capacity of plant 3, I should be better off by $72. My cost should be lower by $72. Do you agree with that? Well, let's test it out. When we ran the solver model, we got this answer. So let's go ahead and use solver table now. And I'm just going to make a one-way table because I just want to test it out. All right, my input cell is going to be the capacity of plant number 3, because that's the one I just did the math on. All right. So free capacity. And I'm going to start at 500 because that's my current value. And I'm just going to go up to 600 in increments of 10. So I'm just going to look at 10 additional units of capacity each time. And for my output cells, I'm going to pick on my objective function, all right? And then the other thing that I might be interested in is seeing how much this matrix changes. Because I did the math, and I said, I know if this goes down to 99 and this goes up to 201, that's worth $72 to me. But I don't know if any of these other numbers are going to change, right? So I'm going to go ahead and pick up the entire matrix here. Actually, I should have done this the other way. I should have started with, there we go. Okay. So now I'm going to run it. And there's my answer. And why did it not change? Well, it did change, right? 175, 330, 174, 610, 173, 890, 173, 170. But look at what's changing. C15. And C15 is plant 3. So yeah, C15 and C14. So C14 is dropping by 10, and C15 is increasing by 10 every time. And since 1 unit was worth $72 to me, 10 units would be worth what? $720, right? So when I do this math here, I get 720. See where the 720 comes from? Okay. So that, in fact, does show me that there is a one-to-one trade-off between capacity of plant 3 and units shipped from plant 2 to region 1. Is that a valuable economic insight? I would argue yes. I would argue that as long as you can increase capacity for less than 700, for less than $72 per unit, whatever your cost is, that you'd be better off increasing capacity of plant number 3 in this case. Is this an insight that you would have come across on your own? Probably. Oh, probably not. I was here I was getting ready to just give you a congratulations and compliment you for being on top of things here. Well, okay, so those of you that are MBA students, or those of you that are MS Finance students, those of you that are MS Accounting students, all right? You're all dealing with money, right? So what I'm trying to do here is I'm trying to give you some clues as to how you can begin to come up with these questions on your own. Right? Solving the problem is the easy part. It's getting the insight that we're more interested in. Okay? We can hire undergrads to solve problems if we need to. Shoot, we can probably hire high school students if we tell them how to do it. But getting that insight, that's where you're adding value to your organization. All right, other questions? know it's hot in here, but you try to stay with me, okay? Other questions? Anybody got any other questions? Sure, I'll be happy to show you how I set up solver table. What I did, you probably followed me up until the last step. What I did was I just chose the capacity cell as my input cell. And I just allowed it to go from its current value up to 600 in units of 10. So I was just looking at 10 separate models. All right. But what I asked it to tell me was the decision value matrix here, C13 to F15, and the objective function value. So I wanted to see how all of the numbers in the decision value matrix changed. Well, it turns out that when solver table ran, the only numbers that changed were, oops, the only numbers that changed were this number and this number. For every 10, every additional 10 units of capacity that I increased, plant 3 went from 200 to 210 to 220 to 230, and plant 2 went from 100 to 90 to 80 to 70. Everything else stayed the same. And just so that you believe me, we can look at the table, the matrix again, and you can see that these numbers are all the same, these numbers are all the same, these numbers are all the same, and these numbers are all the same. The only thing that changed was C14. I'll go ahead and highlight it. The only numbers that changed were C14 and C15. And when I go back and look at those, there's C14, there's C15. There we go. You'll notice that what I just did was the value that gets plotted by the chart is one or more of the output values, okay? In this case, I chose, if you notice what happened there, all of these values at the top here, C13, D13, E13, those are all the decision variables. C21 is the objective function. So what I'm doing here is I'm plotting the value of the objective function with respect to plant capacity. And as plant capacity goes from 500 to 600, which you can't see because the screen cut it off, my objective function goes from 176,050 down to 168,850. What's the slope of this line? Minus 72, right? If you don't believe me, let's go ahead and just insert a trend line. And we'll put the equation in there. And there it is. What else can I show you on this problem? I don't know. Are those the lowest costs? Oh, you mean for this problem? Yeah. Okay. I thought you meant all 4 regions. I was going to say that doesn't sound right. But okay, yeah.